Now, when it comes to aldehydes and ketones, they don't have group C. They have H, or they have the methyl, or it could be an R group, another R group. So they can stabilize by resonance. And then a combination of inductive and steric effects can be used to explain the relative reactivity of aldehydes and ketones. So let's take a look. So this one has an inductive effect because you have methyl. Remember, methyl is an electron donating group. Remember from the last chapter. So methyl is EDG. So what they do is they give electrons toward that carbon. So which mean, again, it makes the carbon less positive. Now this one has two EDGs, not only one, but it has two EDG groups. So what can you predict? That this will be stabilized even more, right? So it would be, there would be even less positive charge. On carbon. So therefore it would be more stable. Which is less electrophilic. So it's not as electrophilic as the aldehyde, which again doesn't make it appealing to nucleophiles. There's also another, so this is inductive, the EDGs, electron donating groups. Now we have sterics. Now what we have here is we have an H and we have a methyl if we keep the acyl group. So you know that the hydrogen is a smaller atom. So in terms of steric, H is less sterically hindered than the methyl. Therefore, overall, aldehydes are more reactive. Electrophilic, let's use that word. Than ketones. Now let's summarize all of what we learned in this table right here. This is a very important table or graph. So if we take a look at this graph right here, it tells you how stable and of course reactive the compounds are. So the least reactive, most stable compound would be the carboxylate anion. That's basically this one. So again, this would be most stable, least reactive. once again, because it's best resonance stabilized, as we've shown before. Acid chloride would be the least stable, most reactive. And what's happening here is you have a strong inductive effect, but weak resonance. So this is important. Keep this one in mind, because you might have a compound that has multiple functional groups, like an acid chloride on one end, a ketone on the other end, or an aldehyde, and so on and so forth. And you would have to choose which one would be most reactive to undergo the reaction from here. So the acid chlorides would be your best bet. The worst one would be the carboxylate anion. And then, of course, in the middle, we have the aldehydes and the ketones. They are not as stable. They are more reactive than the esters and the carboxylic acid. Now, we have irreversible reactions for the type 1. And let's draw this here. So when powerful nucleophiles add to type 1 and type 2 carbonyls, the reaction is irreversible. And this is where we have powerful reagents, and they are the hydride reagents. So we usually put this in quotation marks here, and it's H minus. Hydride, it's basically a hydrogen with 2 electrons. So it would be a negatively charged. It's a very powerful nucleophile. Organometallics are the source of an R minus. So that's where you get an alkyl group or a carbon nucleophile, mostly an alkyl group. And of course, sodium alkanides are from the alkyl groups. We've seen these in SN2, even in the last chapter, as a nucleophile. So that would be the sodium alkanides. Now, briefly, we've drawn this before, but basically what happens is if you have, let's say, a ketone, and let's say you react this with a powerful nucleophile, so you need to remember is that the outcome in the middle would be this. And then one further step to protonate. And you would form an alcohol. So this is irreversible. Irreversible addition reaction. And type 2, and we already talked about this, where Z is a leaving group, can be replaced. So these would come down. Obviously, what's happening here is, in case you are wondering what's happening, we already talked about this. This is the attack. And now basically these electrons would come down, kick the Z out, but wait. What if the nucleophile, the identity of the nucleophile was an H minus or an R? What would happen? What kind of compound would you form at this point? You would form an aldehyde or a ketone. So if I had the nucleophile as R, then that would be a ketone. If I had it as H, then that would be an aldehyde. So aldehyde or a ketone. And now what if you run the reaction twice, one more time? Well, then that step is irreversible. So if we now take this with a nucleophile once more, then we essentially go back. And of course, overall H2O or H3O plus, just to finish that. So if we said, what if the nucleophiles were H or R, then you would get the following. If it was R, you would get an R group there and an R group there. So that's basically a tertiary alcohol. And if you had an H or an H, you can have a primary, or you can have a secondary if you mix. One time you added the R, one other time you added the H. So this second step, this step right here is irreversible.